Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. Again, a reminder that if you do enjoy the show, do please consider supporting us through Buy Me a Coffee. It really helps us to keep making the show. Today, I'm going to be joined by Dimitris Koutsoukos, who will tell us everything we need to know about NVM. Is it not very meaningful for databases? Dimitris is a PhD student in the systems group at ETH Zurich. Dimitris, welcome to the show.
Thank you. Thank you so much for Jack for inviting me here. I'm really happy to be part of this.
Brilliant. So, well, let's jump straight in then. So, can you tell us a little bit more about yourself and how you became interested in database research?
Yes, sure. So right now I'm like a fourth year PhD student in the systems group. I'm just finishing my fourth year and entering my fifth in a month, actually. So I just did this combined bachelor's plus master's we have in Greece called the Masters of Engineering. And then I started working for a couple of years and I realized that I want to do something a bit more than just like being a plain software engineer. And I saw all this this machine plus deep learning boom. And then I said, okay, like the easiest way to get to ride the train is just to do the data science master. And I saw like various universities that offer programs. I just applied to a bunch of them. One of them that accepted me was like at TDH. I took that. And I did a couple of years of like a lot of machine learning, like big data courses and like mathematics courses. And then I realized that I still enjoy like this machine learning part, but to combine it a bit with like my previous background, I like more to like write like code, right? To like work on the systems. And at that point that this happened, I was really interested in like data processing systems that combine like multiple disciplines, for example, like data and relational analytics, machine learning, and this stuff. And that's what brought me to database after all.
Amazing stuff, yeah. So today we're going to be talking a little bit about NVM, right? So non volatile memory. So maybe you can tell the listener, we can go through some background here, and you can kind of tell us what is non volatile memory, also known as persistent memory sometimes, right? So yeah, and let's start off with that. What are these technologies?
So non volatile memory is something I would just like in layman's terms, say, I would just describe it as some like storage layer that is in between traditional hard drive storage, so HDDs and SSDs and DRAM. So it's faster than SSDs. It's slower than DRAM, of course, but also comes at a lower price. It can persist data. The advantage of it is that you can basically use it in order to support the increasing amounts of data that are produced every day, and companies, researchers want to analyze them. Because the problem is that DRAM cannot keep increasing all the time, right? First of all, it's kind of expensive. And secondly, of course, new technologies are coming, but we needed to find a solution to just keeping all the data in main memory most of the time.
Nice. So it sits between kind of SSDs and DRAM and that sort of spectrum. In terms of the price point then, so how much sort of cheaper than DRAM and sort of more expensive than SSD are we talking here, really?
I don't recall the exact numbers. So probably this is a spoiler, but Intel Optane and the commercial implementation of PMEM is now discontinued. So we cannot really buy it or see the price. I would say that probably is 60-70% less than DRAM, in price, 60% of the price of DRAM, just to be exact. Now, about SSDs, there are also NVM SSDs, NVMe SSDs, so it's difficult to just pinpoint it exactly. It also depends on how many SSDs, which is the technology. SSD technology is actually evolving all the time, right?
Right, sure, yeah. So it's quite a diverse sort of thing, so it's hard to draw an exact sort of comparison. Cool. So there's been sort of, you mentioned this in your paper as well, that there's been a whole chunk of research looking at using sort of NVM and PMEM in databases. So where does your work fit into that sort of body of work? And kind of, I guess what's the general elevator pitch for your work in this area?
So my elevator pitch would be that, okay, of course, like we knew that like we cannot keep all data in main memory. And then we started like finding other types like of memory, let's say maybe farm memory, high bandwidth memory, non-volatile memory. And at that point that this idea started, we didn't have like the actual hardware, like any commercial implementation of NVM. And like researchers in databases, but also like in general, did like a lot of studies, right? But at the end, the hardware wasn't there, so they couldn't like exactly see what was happening. Then when the hardware came out, some studies came, but they were like a bit more general, studying the characteristics, like people just like dipped their hands in the water, like very, very slowly. And at that point that we started writing this publication, there were some studies for like not exactly like databases, but like, let's say, OLAP workloads, or like some isolated studies done by companies like Microsoft for SQL Server. But we were like, okay, so let's say that like Jack, you like as a researcher want to come and like use your NVM in databases, and you don't want to like start like optimizing your code, but you just like spend the money or like you found the hardware and you want to see what it does, what it cannot do like for databases, right? And that's how we started to explore, see different workloads, experiment with different knobs, and try to like actually cover breadth and depth at the same time.
Nice. So it's the kind of this paper is the one-stop shop for if you want to know anything about how NVM works in a database, right? It's the comprehensive study. The listener needs to go nowhere else. Just go to this paper. You can find everything you need to know, right? So that's awesome. Cool. So let's talk about the experiments you ran then, because the paper is got a hell of a lot of you've covered a hell of a lot of ground. So let's start off at the very beginning then. Let's tell us about the experimental setup then. So I think we can maybe talk about here. You mentioned it earlier on, about Intel's Optane. So you can maybe start off by telling us about that technology, because that was the actual commercial offering you got your hands on and got to play with. And then we can talk about kind of, I don't know, the systems you measured and the workloads.
Yeah, sure. So just to start and just to make things clear, we studied like Intel Optane in the context like of a database running on a single node. There are many, many more applications. Like in a research paper, is almost impossible to cover everything. And that's like the question like that we try to answer, right? So probably we couldn't fit everything in the title, but like in the context of like a single server, like with a single database, does it make sense to use NVM or not? And there is Intel Optane. So Intel had these NVMe SSDs, which were like faster than traditional SSDs, but of course they were like in the PCIe interconnect. So Intel Optane is actually in the integrated memory controller. So if you like imagine your computer system and you have like your CPUs with the caches, and then you have the memory bus, and then in the memory bus you have the DIMMs that are DRAM. You actually in the same like slots you just plug this Intel Optane technology. So that basically means that it's not like a peripheral device. It's integrated, like the integrated memory controller manages both the DRAM and the Intel Optane. So I would just call it PMEM or NVM just to make it a bit shorter for the rest of the podcast.
Nice. Yeah, there's a few different flavors in which it can be configured in, right? So I think there's memory, AppDirect, and mix mode. Can you tell us about how these differ?
Yes. So in memory mode, you basically substitute in quotes, because it's not like 100% accurate, your volatile memory of the system, so your previous DRAM with PMEM. But the caveat in that is that like DRAM becomes an L4 direct map cast. So basically, you still have like the previous memory hierarchy, but the DRAM is like a hidden cache for you now. In AppDirect mode, there are a number of ways. So basically, PMEM just becomes like another storage layer, like let's say a faster SSD. You can configure it in like a number of namespaces. Intel recommends FSTags, which actually bypasses the operating system page cache, and you can just use directly mmap to map like files to the storage medium. And this is actually the previous studies have mostly studied this mode and not from the angle that we have done. And they were trying to see like how can I adjust my shortcode and like my software to just be able to take advantage of that. And mixed mode is just like you configure a percentage in memory mode and a percentage in AppDirect mode. Intel recommends a ratio of 1:4, I think, just for a price and performance ratio. And DRAM, becomes an L for direct mapped cache. And just like, because I mentioned it, just to also make clear, we just wanted to, when we just benchmarked NVM, we didn't want to make like changes in the source code, right? As I said in the beginning, we just want to say, you just happen to find this hardware somehow. Like, can you use it? How can you use it? What happened?
Yeah, just drops from the sky. Hey, go, okay, now what do I want to do? Right, yeah, cool. So just to recap there real quick. So the in-memory case that allows us to basically swap it out for DRAM. DRAM becomes a hidden cache, but we have the same memory hierarchy. Whereas AppDirect, that allows us to sort of interact, and we can map directly. And mixed mode is kind of a combination of the two. And they recommend it was a 1:4 ratio. Which was the 1 and which was the 4 in that ratio?
I think so for 1 gigabyte of like DRAM, you needed 4 gigabytes of like PMEM in memory mode, if I'm not mistaken.
Gotcha. Cool. That makes sense. Cool. Great stuff. So this is the toy that you've been playing with for all these experiments. So now that we've covered that, so let's talk a little bit more about the experimental setup then. So what were the systems you used, and then maybe you can introduce some of the benchmarks as well. I know we're going to talk about those in a lot of depth later on, but yeah. Give us a high-level sort of overview of all the various components.
Yes, sure. So we just like, I don't know, like we're database researchers, right? So we know 2 types of benchmarks. We know OLTP and we know OLAP. And at the end, we chose like an OLAP workload like TPCH. It's heavily used, especially when it's the first thing that you want to do, like in a research paper. Also, companies just use it as like, I don't know, like a point to prove that like they have an efficiency.
How fast we are.
Yes, exactly. And for OLTP, we used TPCC. It's also like very, very heavily used. And then at some point, one of the reviewers asked for key value stores just to like bridge like all the different types of relational databases that we could have. I know like key value stores are not exactly like a database, but they are used as kind of such, right? So we also like the most famous benchmark there is like the Yahoo Cloud Streaming benchmark. So we also ended up using that. And for what we tried to do in general is that we said, okay, like we really need to stress the memory, right? And we know that maybe some of the effects that we see are a bit exaggerated because we stressed the memory in cases that it's not common. But we really wanted to see like the weak points, the strong points. So we just isolated all our experiments in one NUMA node, so that we made sure that our working set is actually higher than the amount of DRAM that we have there. So basically, we wanted to use as much PMEM as possible for the experiments that we run. So for TPCH, for example, we would use scale factor 100. For TPCC, we configured the number of warehouses to just have around 100 gigabytes of data, and the same for the Yahoo Cloud Streaming benchmark.
Awesome, cool, yeah. So which systems did you use then in these experiments?
So in the end, we ended up using, I think, 5 or 6 systems, not for all benchmarks. So for OLAP workloads, TPCH, we used PostgreSQL, MySQL, SQL Server, and then DuckDB. And for TPCC, we used, again, Postgres, MySQL, SQL Server, and VaultDB. And for the Yahoo Cloud Streaming benchmark, we just used RocksDB.
Nice. What drove the choices of those systems? Did it just to get a breadth of some of the most popular systems? And I guess you've got a nice, obviously, cross-section there of transactional systems, also with obviously analytical systems as well. But was there anything more to it than that?
So the first choice is that we wanted to focus on as much of open source databases as possible.
Sure.
Because as you well know, it's very easy to change configurations, understand understand the behavior, because you can actually have access to the source code, right? And understand how they manage the different stuff. So this was the first choice that we made. So that's why we chose the Postgres and MySQL, and also DuckDB. I think that are three of the most popular systems that are being used in databases now. And then we also use SQL Server because we know that I don't know, it has of course I agree with that it has a very high place in the industry, for optimization of plans, running queries very fast. And for the the VoltDB, I think we chose it because we also wanted to a specialized, let's say, OLTP system. Of course, MySQL is one of them, but you wanted a second one because Postgres and SQL Server are not so popular for OLTP workloads. And for the Yahoo Cloud Streaming benchmark, I think we just picked RocksDB again because of being open source and popular, right? We just wanted a key value source that people actually use a lot. And also the other studies have used a lot RocksDB as well for comparisons.
Yeah, cool. Yeah, and obviously you scoped here kind of on relational systems, but did you ever have you thought about maybe how this experiment would interact with maybe kind of some of the systems like MongoDB, for example, who's a little bit sort of out of the usual sort of relational world?
We thought at some point to do experiments with NoSQL databases like MongoDB, for example. But the thing with these systems is that they don't have such standardized benchmarks, at least in my experience, as Postgres or MySQL. And then it's hard, first of all, to find the insights, because if you don't we discussed about TPCH before, right? You know the benchmark by heart, you know the weak points, you know what happens. We need the benchmark like that for MongoDB. And also in academia, you also need reviewers, the other side, to be able to understand and contribute with their comments to that. So it was I don't know, it was just a compromise at the end, right?
Yeah, sure. I mean, at the end of the day, right, you've got to be practical about it at some point, right? Because there's that many systems. You'd be doing it forever, and at some point you've got to publish, right? So, I mean, that's really cool. So let's talk about some results then. So just kind of set the scene. You ran some sort of baseline micro benchmarks. Can you tell me what kind of these were and kind of what some of the sort of preliminary sort of findings were of those experiments?
So these micro benchmarks, we just had them as a point of reference. There was a lot of work in basically more in systems conferences, let's say, and especially there is a famous lab led by Swanson that have open sourced their code as well. So me and the other people that worked on the paper here, it was a postdoc, Michael Friedman, that took more of the micro benchmarks. She took the code of these previous papers, he adapted it in order to be able to understand what are the limits, right? The how faster, in practice can PMEM be than DRAM or than the SSD that we had. And of course, we could do that only for the just this parenthesis here, and just to bring probably the audience in the same page. Memory mode is we know the basics that I said, but it's kind of a black box, right? We don't know exactly how it works. We do not know we know that it's direct math, but we cannot pinpoint exactly what is happening there, right? So when we run these micro benchmarks, we couldn't verify that what we are actually seeing as a behavior was actually the memory mode and not something else that was hidden behind the scenes. So the micro benchmarks were not for memory mode, but just for the AppDirect mode, our SSD and DRAM, which I don't know, we were perfectly clear that, okay, this is what happens with these hardware components. And we can be sure that, for example, PMEM has 10 times more read and write bandwidth than the SSD.
Cool. Let's get into some of the OLAP experiments then. So can you start maybe giving us sort of some of the sort of the general insights, the general observations you found whilst doing this experiments with TPCH?
Yes, sure. So I would say that the 4 different databases that we had gave some common insights and many different insights. What I would say, one of the common insights is that when you have a workload like TPCH that you mainly read, the more cores that you use, the better you get, the higher bandwidth you get for PMEM, and you reach like the maximum both in PMEM and DSSD, and you can see like a lot of difference. But on the other hand, we didn't see like the exact difference that we have seen like in the micro benchmarks. And we were kind of like wondering where this, why this happens, or where some of the bandwidth is lost. And then we started observing how like different databases like Postgres utilize the page cache, the operating system page cache. And we saw that because PMEM is in the integrated memory controller, then there is no direct memory access, right? There is no like this kind of prefetching that is happening through PCIe, that you know that data are going to be there. So you just prefetch them in the operating systems cache and page cache, and the database reads them from there. And the CPU has to be like involved all the time. So you're kind of losing some bandwidth there. Another insight that we got is that for some reason, it's also like very known online. If you use any search engine and you search for it, SQL doesn't use more than one core for analytical queries, except for a very specific type of queries. And you cannot really change this behavior. So in very constrained environments, we saw that the advantage of PMEM was like even less, because you had to spend some of the CPU resources to do the processing. You had to spend some of the CPU resources to actually transfer the data through the integrated memory controller. So you were losing a bit of that as well. And that insight was also verified by DuckDB. DuckDB, like from all the systems that we run, is very like has a columnar format instead of a row format. It's like very optimized for specific type of queries, especially TPCH. And we saw that for CPU intensive queries, for example, because it's a columnar format, and anyway storage of course plays a role, but you don't read as much data as in like in a row format. You can see that PMEM in AppDirect mode is more or less the same as like using a plain SSD, or sometimes even worse. Just to make things clear, what I just discussed before is mainly about the AppDirect mode, right?
Okay, sure. So there was obviously, you mentioned earlier, there's various knobs you've changed in some of these experiments to sort of investigate different areas of this sort of space. So can you maybe talk us through when you were doing your experiments, which knobs you did vary?
So in general, we try to like make the buffer cache as small a size, but like of course we wouldn't make it like 1 megabyte, because that wouldn't make sense. But like we wanted to use as less of DRAM as possible, right? So we made it like 16 gigabytes. We experimented for like other sizes, but we settled up on that at the end, in order to be able to just read from disks all the time. Disk being either PMEM or like an SSD. We didn't actually experiment with it, but we saw how like Postgres utilizes a lot like a cycle buffer in order to be able to just get data and process them. And I would say that like for OLAP, we mainly focused on trying to understand, okay, your database has a query plan that is like an aggregate that is based on like a hash table, and then like a double for a loop join. So we were trying to understand, okay, how like would this map to like the actual hardware characteristics, and like what it makes sense to change, like making the access size larger, or like the block size larger or smaller. So I would say it was more like observation and less experimentation compared to TPCC, that we like had a lot more room to just tune knobs there.
Okay, cool. So I guess that's a nice segue into the OLTP experiments then. So I guess let's rinse and repeat here. Tell us about the insights, and then we can talk about the various knobs.
So something that we also observed for OLAP, but it was more obvious for the OLTP, is that memory mode, it has some like tiny few cases that it was better. So you needed to have like workloads that not only had the larger working set than DRAM and the OS page cache combined, but you also needed to have like a slow number of read and write accesses to them, right? So let's say that you have a table, it's very large, you read it once, you process it, and then you're done. You're not going to read it multiple times. So was like the premise for memory mode. But for OLTP, we really didn't find like anything that it could be better compared to a system that uses a plain SSD and just DRAM, and then that's it. We also saw verified insights that other people have found. For example, that you need to be very careful when you do write and read workloads together. So we had to make sure that like the interference, and how the queues are managed by the integrated memory controller made sense, right? Because the thing is that with PMEM, when you have like just read workloads, the bandwidth increases like almost indefinitely until you get to the maximum. But as you increase the write rates, there is a lot of contention, and then the bandwidth drops. And there is, if I can describe it, it's an opposite U curve. It's basically not an opposite, like a proper U curve with the read and write workloads. You have like a sweet spot in the middle, and then you end up like thrusting left and right. So that were the two main insights, I would say. So be careful when you have mixed workloads. When you have write workloads, also be careful. Don't write too much, because then you will also have bad results. And at some point at DPCC for SQL Server, we had so bad results when we were using a high number of users that the SSD was better by a large margin for the transaction rate.
That's crazy. I mean, obviously the elephant in the room here, you mentioned it earlier on, is that they discontinued this now of Intel. So is this maybe the reason why, right? Like the performance of it just isn't that good. I mean, obviously, I know it would be used for a lot of other things than just databases, but I mean, this doesn't seem like, it's not kind of a glowing sort of endorsement or use case. Like, look how amazing it is, right? So yeah, do you have any sort of information on why they discontinued it?
I know the speculations that everybody
let's speculate.
don't know lines. So I don't really know why they did it. I guess that one reason was that, right? And one other reason was the cost, because it had a kind of a hidden cost, let's say. Because basically, besides having a PMEM, buying PMEM and putting in your system, there is a certain number of Intel processors that can actually support PMEM, right? You cannot put your processor from 6-7 years ago and expect it to work with PMEM out of the box. So it was a combined hidden cost, I would say. There were some of the companies that were also producing these chips, because Intel outsources the production of the actual circuits, that were also not so happy economically. That's what online sources say. Combined with this characteristics that don't make the software so appealing. And I guess this was the final push to push to this direction. And also there was this CXL, the Compute Expressly, which is being advertised as the new solution. So it was just tiny bit pieces that were at the end.
Yeah, in the end, it's the straw that breaks the camel's back, right? There's all these little sort of minor sort of cuts, right? And then death by 1,000 cuts. There's another saying for it, I guess. Cool. So we've touched on some of the general insights there from the OLTP experiments. But yeah, you said that you varied a lot of different knobs here, tuned a lot of different knobs. So let's talk about the things you varied when you were doing these experiments then.
Yeah, so we just played first of all with the number of threads that you can use when you want to write, for example, and we observed what other people have done. There are optimizations in Postgres the wall compression, and it's used to just compress the logs in order to take advantage that CPU is actually faster than storage. But there we just couldn't see any advantage of it. So all optimizations have to be reconfigured or rethought a bit in order to be able to just bring them into PMEM. We also saw in MySQL the number of flashing methods, because MySQL you can just you have different ways to be able to flash your logs and your data to storage, right? You can do it again by passing the page cache. You can just use intermediate buffers. So we also played a bit with that. And we also, so in general, like in AppDirect mode, let's say that you have, it's like bus of the integrated memory controller. You have like, let's say one like slot of PMEM, right? There is a way to combine them together. And this is called interleaved AppDirect mode, but there is a way to just see them as two separate namespaces. We also played around a bit with that. And finally, we just went a bit around. And so like, let's store the logs in like one storage medium, let's say SSD, and the data in another storage medium, for example, PMEM, or store everything in PMEM or in everything in SSD. And to understand like if you can gain some performance advantage, or because like, I don't know, Intel Optane and PMEM in general are being like advertised a lot for persistency. And you can say, okay, and I want my logs to be persistent, right? So what if I just store the logs and not like everything there? But in general, besides like we had some like insights that other people had, but like the other insights just like followed a bit naturally with the general story of like the paper and the weaknesses that we had identified before.
Cool. Yeah, I guess so. Given that, then moving on to the key value experiments and YCSB, was that the same story there, or was there different sort of insights that you got out of those experiments?
It was just like a confirmation of the story that we have seen before. We used like 3 workloads. One was like half and half, so mixed. And there we saw like actually that with mixed workloads is like very, very tricky. And then we had just a read workload, which showed like that. I don't know how you can use PMEM and just expect like your bandwidth to grow indefinitely up until like a very high point. And then mainly write workloads. So I wouldn't say that there was anything very surprising. The difference is that there the keys and the values were very wide. And we were expecting maybe to get some performance advantage because the line of PMEM is like 256 bytes, which is like 4 times larger than like a line in DRAM, for example. So maybe we said because of read and write amplification, we'll be able to see like some different behavior, but we couldn't like identify something that wasn't like revealed in part in the previous part of the paper.
Yeah, of course. I'm getting the answer to the question, and the title of the paper is "No, it's not very meaningful."
That's yeah.
Cool. So I guess before we move on to sort of some more kind of, I guess, general questions about things, it might be a good opportunity just if you would like to provide like a summary of all the insights you sort of found, or like kind of condense all your findings into sort of one soundbite, I guess, if you can do that. I mean, there's a lot of findings, but yeah.
So if I wanted like, I don't know, listeners to just like think about 2 things like from this paper, the one is that the memory mode, like we couldn't really find like a use where like it's science or you should use it if you have like a shortage of DRAM. The second one is that the AppDirect mode is more optimized like as a hardware from like a traditional SSD, but like there are small caveats along the way. So you should be careful about read-write interference, the number of write threads, if your resources are limited, for example. So if your system like Postgres uses a lot the OS page cache, because then other systems, I mean, when you just use an SSD, this might cover some part of the hardware difference. So these are all the things that a reader or like a researcher or some person like working in a company should pay attention to if they use like Intel Optane at some point in the future.
Cool. That's a nice summary there. So I guess, are there any sort of limitations of your study though? So I mean, obviously it'd be very sort of comprehensive, but are there any areas of it where you think, yeah, that could maybe have been improved, or this is some of the dark corners of the study that we kind of pushed to one side? I don't know, but yeah, are there any limitations, I guess, is the general question.
Yes, of course, like every study like has limitations. So like my paper is not like an exception to that. I have heard from people in companies that like when they use like PMEM as like in a separate machine as like a caching layer in the cloud, they get like a really good results compared to traditional SSDs. No, but our study was like more on like a single like server environment, and it was hard to push the scale factor and everything to the extreme because you wanted to be able to fit like in the hardware that we had. So you wanted to be able to fit everything into one NUMA node, which means 256 gigabyte of PMEM, 2 terabytes of SSD plus like 64 gigabyte of RAM. So like at the end, like the scale factors were just a bit restricted by this fact, right? Maybe like if you go like you have like I don't know, like a system that is like has like a few terabytes of RAM, and then you have like again a few terabytes of PMEM and like more optimized SSDs, you will find, of course, you will find some of the findings that we did, but like maybe you will find some things that we missed.
Cool. Yes, I guess kind of on that then, is there any sort of plans for the next steps of this study, or is it with this technology in general with PMEM, or is this kind of the end of the road for PMEM for you for now?
For me, yes, this is like the end of the road after the discontinuation. With CXL, because right now like it's simulated using FPGAs, so field non-programmable arrays. And my group had like a long tradition of using this type of hardware. I think they are planning to do some CXL work. I'm not so involved in that. But for PMEM as it is, we really don't have anything to continue working on that line of research.
Sure, cool. I guess kind of you mentioned it a bit early on actually about sort of what you would want a software engineer or DBA or someone building kind of a database system to kind of keep in mind from your study. But I guess what I want to know is what impact do you think this your work can have, and maybe what impact it has maybe had already, if you've had any sort of feedback from people who've used this study to influence what they're doing in their day-to-day work.
When I was like presenting to VLDB, it was like it was kind of like a nice surprise, let's say. There was like a very known researcher for Microsoft, and he said that look, like you don't present us anything new, right? At Microsoft, we had the software from 2019 when it came out, and like all the things that you have said, and that it's not like so useful. We have found out the same things, right? And like at the end, that's why it was discontinued. And then like I told him like that, look, like when we were writing this study, like it was like more than a year before the technology got discontinued, and like by the time that we submitted it for the first time, it was also like more than like 8 months before it was discontinued, right? So then he understood like the motivation of our work, and like that we had actually like predicted in a way like the discontinuation without knowing it.
Yeah, that's funny. I mean, but I mean, it's all good and well them knowing internally at Microsoft that this is the reason why and this is what. But I mean, not everyone has access to the resources Microsoft do to figure this out, right? So you need to kind of have it in the public domain somewhere to sort of to allow other people to go and sort of get the same insights, right? Because these big companies are very good at keeping their findings to themselves. I mean, no, I think it's really good work, and yeah. I think hopefully you got your point across to him.
Thank you so much. Like I don't know, like it's a bit of a win, let's say, at the end that the history just confirms what you have predicted, right?
Exactly. Yeah. So it's great. That's cool. Awesome. So yeah, another question I like to ask people whilst when we're talking about the work is, was there any sort of I don't know what. There's two sort of angles to this question. The first is kind of what is the most interesting thing that you learned while working on NVM, other than the fact that you can predict the future?
The most interesting fact, I think, that there is this like specification like book that we see for every type of hardware, but the reality sometimes surprises you, right? This was like for me what was the most interesting thing when I was working with this technology.
Cool. And I guess on the other side of that question, then, kind of, what was sort of the most the unexpected thing, or maybe the thing you tried along the way that failed, and that was kind of like, I don't know, some war stories, I guess, from this project? Because you said you were working on it for quite a long time.
Like, first of all, it was like kind of like a war story to like get this like paper accepted, because it's like of course like the title is a bit controversial, the results were a bit controversial as well. It's hard to convince like people so like easily that like something that has been elevator pitched like for decades, right? And like it's actually now it's not like really worth the fuss. I would say that like this was one of the struggles in this work. And also when you are using so many systems and you like have to conform to all the dependencies and stuff like that, this is like a bit different than your like typical database paper that you develop a solution, you have like a couple of baselines, etc. When you are using like 6, 7, 8 different databases and version change, the way that they work changes, like it's kind of hard to like synchronize and script everything like in one place.
Yeah, every system has a different way, of different syntax for doing the same thing, right? So yeah, it's a bit of a nightmare. I can imagine that was a very difficult challenge. Cool. Yeah. So I've just got a few more questions now. So I guess the next one you've mentioned it at various points throughout the podcast, is that some of the other research you work on. So can you maybe tell us more about some of the stuff you've maybe done in the past and maybe some of the stuff that you wish to do in the future?
Just like to take like a pause here, since we're just switching. Like I would like to thank like a lot of like the people that work in this paper.
Yeah, go for it.
Yeah, I would like to thank like really a lot Raghav Bhartia, the second author. He was a master student at the point that we started this work. I think he's now doing like a very good career like as a software engineer, but he really worked and like produced together with me many of the results that we actually found like in the paper at the time. And like I remember like the conversations and some of the things that he was saying to me, and I was like skeptical at that point. And then but like at the end he did like excellent work from like his master's thesis, right? And just like to share like about some like future plans and in general like the motivation of my like PhD and my dissertation. I was just like my main, let's say, the main research question that I was trying to answer is that, look, like the data processing landscape like evolves very fast. You have like new types of hardware, new types of algorithms. You want to have like real-time processing. Your data is increasing, and usually the systems that are built right now are like a bit monolithic, like are a bit like very good at doing exactly one thing. They're super fast and doing this exact one thing. But the moment that you have to change something, you basically have to rewrite everything from scratch. So I just pick like different like parts and see how we can adapt them to like the modern trends of like hardware or platforms. And my work is just going to continue like at the same, let's say, road. I'm working right now to a bit like how it's again on storage is how we can like optimize the storage that like query as a service systems use. For example, BigQuery, Athena, or even like Snowflake and Databricks, but like a bit more of the first two for like a workload that you have in order to have like the best latency and also the best cost. So a bit like more like since the data processing moves in the cloud, how you want to organize your data to take advantage of that. And another type of work that I'm kind of doing is bridging, like other people like do this type of work as well. But I would say I'm like doing it from a bit of like a different angle. So I had like a system that I built like as part of my PhD. It's called Modularis. And at that point, it was just doing like relational workloads. And we now extended to machine learning workloads. We added the support for FPGAs to be used like as a smart storage engine. And we want to see how you can build like a system that is like using different types of hardware to just run one query, right? Because maybe like as you said before, we don't know like what comparison system do. Maybe Amazon Redshift does the same thing, but like when you just develop like your own system and like you open source it afterwards, you know exactly how these things work from like one system from another and how you can like put them all together.
Yeah, so it sounds like you've got loads of really cool things to be working on there. So I'd love to know about how you actually approach generating these ideas and things to work on. And then obviously once you've generated the ideas, I mean, selecting the things to actually dedicate a significant portion of time to.
Basically, I think it's just like an iterative process, mainly like based on discussions. I've been like extremely lucky to have like some very talented like colleagues in my group. and maybe somebody will tell you, okay, like we have this, for example, have this problem, and like how will you solve it? And then you start thinking that this is actually like a problem, right? And maybe some of these people like go to industry afterwards, and you see that like if you still keep in touch, you see that this problem actually exists in like also companies. So like, for example, this like evolving data layout or like to optimize your data layout based on like workload, it's like a real problem, right? So like let's say that you're the typical data scientist of today, and you have like your data somewhere in whatever, like CSV, JSON, Parquet. I mean, if you want to do some analysis, probably you won't have like a full-fledged database, right? You would just like use a query as a service system. Then you would just run your queries, take some insights, take some rows, like compute what you need to train your machine learning models or whatever. So given the fact that you know this, and like you don't to pay like so much money every time to like Amazon or like Google or whatever, what can you do to just say, okay, I want to like take advantage of like some transformations that I know make sense for these systems, for example, compression, to be able to have workloads that run faster and are also cheaper. And also like, also this is the typical like data scientist problem, right? So you want to like, let's say, have a model that does a prediction. You will just go to like a database, then you will have to run something, then you will export your results to CSV, Parquetization, then you will just start using Python, you will import them to pandas, you will start training your scikit-learn model. So what if you can do all of them like with one system? And what if you can do it like using different types of hardware as well?
Fascinating. I really liked what you were saying in the answer to this question about sort of the people you surround you with, right? You really are a kind of product of your environment, right? And if you surround yourself with good people, then I know it just produces those good ideas. And if you can iterate on things as well, yeah, no, that's a great answer to that question. So with that, we're on to the last question. I know you gave a great summary of your work on NVM earlier on, but maybe now is a chance to get to give that message again. So what's the one thing you want the listeners to take away from this podcast today?
The one takeaway that I would say, like, so first of all, like in the context of NVM, like today, there is no NVM, right? This technology is discontinued. I hope that my study will just give light for like future types of hardware that will be similar to NVM or even CXL, right? To just not have some of the weaknesses that this system had. For example, what I discussed about like using CPU to just read all the time and not having DMA, or not having like a hardware prefetcher that like brings data to your main memory. Just like take it as lessons in order not to do them, like see what NVM did wrong, and don't repeat it. That's I would say it's like the main takeaway.
Yeah, which was the saying, something like, if those who don't understand history or know history are doomed to repeat the failures of the past or something, right? So yeah, there's a warning message there. So yeah, great stuff. Well, that's great. Let's end things there. Thank you so much, Dimitris, for coming on the show. It's been a fascinating chat. If the listeners interested in knowing more about Dimitris' work, we'll put links to everything in the show notes so you can go and find that. And again, if you do enjoy the show, please do consider supporting us. It really helps us to keep making the show. And we'll see you all next time for some more awesome computer science research.